in the graduate community, which I really appreciate. When Gabby first came, I wanted her to work at the Andrews, had some funding available, and I first pitched the idea along with Mark Schultz, your co-advisor, who will talk shortly, about analyzing, there's a huge amount of dendrometer data we have from the Andrews, from these little electronic things that you'll learn about. And if you know about them, you know that they're incredibly useful, but if you know about them, you also know they can be incredibly frustrating to work with the data. There's a lot of nuance required. And so Gabby really went at that eagerly, even though I'm not sure she'd even heard of a dendrometer before she got here, because Oklahoma doesn't have a lot of trees. Sorry, Gabby's family. I can say that because I actually did some of my PhD research in Oklahoma and grasslands, so I know there's not a lot of trees there. But anyway, she attacked the problem eagerly, and I think just, again, exemplified this sort of wonderful personality that she has. She's been a joy to work with. Along the way, she's learned a huge amount of stuff from diving into R programming. She thinks she knows a little bit of R, but nothing like she knows now. Nothing. Okay. So she's in Excel. So that's a steep learning curve for those of you who've used R, which is probably most people. She learned lots of data analysis and working with instruments, and also tree coring and tree analysis and all sorts of things. And before I hand it up to Mark to talk about some of the challenges that Gabby had to overcome in this, I want to note also that at 5 p.m., if you can make it, we're meeting at Squirrels downtown for a happy hour to celebrate Gabby. So please do join us there if you can around 5 p.m. at Squirrels downtown. And with that, I will pass it off to Mark to finish and introduce the other panel.
Yeah, I just wanted to compliment what Chris said about and add some of the attributes that I'm most impressed with from Gabby. And those are in particular her perseverance and her equanimity. And to put that into context, so she had done her first year of coursework. Summer of 2024, we were going to ramp up the research, get her out in the field. I had great visions. Okay, we're going to go out, get her hands on dendrometers, get her develop a personal relationship with them. We can have long philosophical conversations about what dendrometers do like to reveal and what they like to keep hidden, and get her really set up to do this analysis. And I think we got you out really briefly for one trip before ore fire broke out. And that was game over for field work for several months. And I also disappeared into a vortex, only to be able to pop my head up every once in a while to make annoying comments about what was coming out on the analysis. So what we decided as a plan B was, okay, why don't you get to know dendrometers by just diving into the data? And we had read a paper that had like this really cool R script, it was published. Must be an amazing R script. Why don't you just take our good ecomatic data and start playing around with the R script? And I'm sure it's amazing R script, but it was developed in a different part of the world for different trees and different style dendrometers. And so it was producing complete gibberish. It was really good at taking perfectly good data and making it totally unusable. And so we said, okay, well, but it's a great program, so maybe it's just not the right type of dendrometer. So Chris had bought into the Tom's line that these point dendrometers that are super cheap must be pretty good, better than the good dendrometers, in my opinion. And they're point dendrometers, and the program was designed for point dendrometers. So okay, we'll try that. And maybe we'll figure out how to make this program work, and then it'll be just smooth sailing. That was even worse in part because the Tom's are great except when they're completely worthless, and it's about 50-50 in my experience. And sometimes they start off great, and then you turn your back on them, and they start doing gibberish. So then we said, okay, let's go back to the first set of dendrometers, and let's look for a new R script. And so through all this time, Gabby would have been well within her rights to say, I want to do my master's on anything but dendrometers. These are terrible. But through this whole time, I don't know what was in her head, and I probably don't want to know what was in her head, but this whole time, she just radiated this positive attitude, and she would go back to the drawing board and try again. And even when we had a program that worked, she had to do a lot of fine-tuning to make it work. So really impressive that what you're going to see, it may look like, oh, yeah, those are easy graphs, digital dendrometers, but it was hard-fought data. So.
Oh, thanks. I had no idea that that's what was going through your head. I had no idea. That process of trying different programs and things was probably 5-6 months of just time. And like Chris said, I didn't know anything about R before coming here, so it was actually really great practice to figure out what was going on. And looking back on my code now, it's like, oh, no. Anyways, well, that was really that. So now this is gonna be great. I know most of you because we're pals. Others of you are future pals at the Andrews Forest. I'll talk a little bit about the Andrews, but I won't get super into why it's such a big deal and such an important place to be, but just know that it is and that it's really special. And so, sorry? Oh, I think it is on Zoom, yeah. Yes. So without further ado, I'll try to have us done and ready for questions by like 2:45. And then after questions, I'll have a little really short video collage that I made to kind of summarize my time as a master's student. So if you don't care about that, you can just leave. But in the meantime, we'll get into science. So yes, my name is Gabby John. I'm going to be graduating at the end of this term with my Master of Science in Forest Ecosystems and Society in the College of Forestry here at OSU. And my main question and purpose of my thesis is to investigate how two main trees of Oregon, Douglas fir and western hemlock, respond to extreme heat. And, okay. So to do that, we're going to go through kind of 6 sections, a background on my research topic, my specific research questions, a brief overview of the stuff that I had to do to get there, and mainly results, and then some take-home messages and some concluding remarks. So first, the background. I'm sure in Oregon, we all can agree that trees are really cool and trees are really important, and the way that they interact with the environment is also important. So trees are good for many things. From a climate change and environmental perspective, they sequester carbon dioxide in their stem. Up to 75% of a tree's biomass is just in the stem. And carbon dioxide, being a greenhouse gas, can trap a lot of heat in the atmosphere. So the more carbon that can be taken from the atmosphere and stored in a tree can have mitigating effects on climate change. But there are some severe and common and long-lasting record-breaking weather events that have been happening in recent years, and models and projections predict that those will increase both in frequency and severity over time. So it's important to study how those cause trees to have some different physiological reactions. And for heat stress specifically, it affects how trees can resist other stressors. So you can kind of think of it like an autoimmune condition, where if the tree is stressed out from something like heat stress, it can lead to other negative impacts happening for the tree, like different diseases or pests and things like that. And all of this affects how trees add new biomass, both on the individual scale and also the ecosystem level scale. And so, as you can imagine, with all of that being said, research on the relationships between trees and heat stress can have implications for forest management or people setting up carbon budgets to predict where carbon will be in the future, and ecological risk assessments to think about things like where species might be located in the future. So our research is basically a huge case study of the 2021 heat dome of the Pacific Northwest. It was, in pretty much all definitions of the words, unprecedented, catastrophic, and lethal. It was a really intense heat wave affecting the Pacific Northwest during peak growing season, so late June. Dozens and dozens and dozens of papers have come out about this. Like, it really cannot be overstated how important of an event this was. Thank God I did not live here at the time, or else I would have had a really bad time. So my heart goes out to all of you who did live in the Pacific Northwest during that time. Now, even though there is a lot of research that's been done on the topic, there's still so much more to be looked at. So our research addresses some gaps like an in-depth and high-resolution or high-frequency view or case study of the heat dome, and specifically tree growth during the time. A lot of the significant impacts were damage or burning or scorch of the leaves of trees. You can come in if you want to. Oh yeah, thank you. Hi. Yes, perfect. Also, tree responses to the heat dome varied widely. The Pacific Northwest is a really big region. So there are different species effects, different forest effects. I mean, as we will learn, these kinds of things in forest ecology are so specific to the individual, to the genetics, to the specific growing environment. So in my opinion, you really can't overstudy things like this. Okay. There's also a generally poor understanding of heat waves as a separate event from drought. They usually happen together, but they don't always. And the effects that they have on plants can be very different. So it's important to have a study like this where we have a really high resolution view of kind of what's going on within the tree level so that we can see kind of different impacts of different types of microclimate or heat and drought. In the last few years, there have been a lot of technology and software, like Mark talked about, to analyze data for really, really intense and really, really large data sets. And so there's an opportunity to kind of test the limits of these software applications and think about how they can be used or modified in the future. And there's also not a lot of studies that run a large variety of different scales. So we are pairing really, really high resolution dendrometer data, and I'll explain what that is, with much longer term records of tree rings and kind of pairing the two together to have both short term and long term views of tree growth during a really intense event. So for my master's degree, I have 3 specific research questions. The first and main one is asking how the heat dome affected western hemlock and Douglas fir growth at the H.J. Andrews Experimental Forest for the remainder of the 2021 growing season when it happened, as well as subsequent growing seasons. These 2 trees were selected because they are 2 of the most dominant tree types in Oregon, but especially the Andrews. And the Andrews, oh well, never mind, I'll talk about that. My second question is seeing if there are specific types of microclimate variables that might correspond better with these patterns of tree growth. And then the third one is, like I hinted at, zooming out, bigger picture, seeing if tree rings and the much larger records that they hold correspond with the data that we have analyzed and that we are observing in our dendrometers. So the Andrews is located in central-ish Oregon, western central Oregon. It's a moist valley in this area with a Mediterranean climate, which means that there are cold and moist but relatively mild winters, and relatively mild by Oklahoma standards, but hot by West Coast standards, and dry summers. Which can be really hard when it comes to analyzing data, because a lot of other places, especially places that are designing these software applications, their growing season does correspond with the rainy season. So they might say like, okay, if the tree is expanding, that has to mean it's growing, which isn't necessarily true. There are a lot of really old trees at the Andrews, which has been so nice for me to see, because like Chris said, we might have like an oak tree here and there in Oklahoma, but the idea of just like casually studying and being around a 400, 500-year-old tree is so nice and so special. And so there are those that we have in our data that we'll be talking about, and there are also some younger ones, but still getting into what's classified as like a mature age class for both Douglas fir and western hemlock. These measurements are taken every 5 minutes and have since at least 2018. So, I'll like talk about that a lot, but just, it's a lot of data. So let's talk a bit about stem behavior. So in a tree, water starts in the soil and enters the roots, and it travels from the roots through the tree and out through the leaves. And all of that happens through the xylem, which you can think of like the blood vessels or like the vascular system that we have in our cells. There are different types of expansion that can happen in the tree stem as water's moving through the xylem. You can see there's this circle right here. This can be like a top-down view of the stem, where this is growth of the bark and expansion of the bark. And this can either swell or contract. And that happens as the result of changes to the stem circumference that can happen throughout the day as the air gets either hotter or warmer, or hotter or cooler throughout the day. It's a very elastic process. So that kind of leads us to 3 different expansion cycles. So there's shrinking, which can happen if there's a lot of transpiration happening, which is that process of water moving through the roots and out through the leaves. So that can kind of lead to an expulsion of water, which leads to a contraction of the stem. And then there are 2 different types of swelling. There's permanent, which is actual growth and permanent increment, or there is non-permanent growth, which can be the result of just like water swell, like I talked about, kind of like bloating, I guess. And dendrometers measure these changes in that stem size on microscopic scales. So the raw data that we download from the dendrometers record in micrometers, and 1 millimeter is 1,000 micrometers. So it's like really teeny tiny, which it better be if it's getting a new measurement every 5 minutes. It's really small things. So this is a picture of a dendrometer. We have 11 trees with these, so it's this little band right here with the blue beads on it. So it wraps around the tree stem and the circumference, and there are 11 trees at the Andrews, near the southwest side of the Andrews, along what's called the Discovery Trail. So we have 11 of these. There are 3 old growth Douglas fir, so those are going to be like the really, really old ones, like 400 plus years old. 4 second growth Doug firs, so those are going to be like the more 75, 80-year-old ones. And then there are 3 old growth western hemlocks and 1 old growth western red cedar. Processing all of this data, millions and millions and millions of rows, requires a lot of attention to detail and some sufficient software, which is one of the goals, is to kind of test the limits and really see what some of these software applications are capable of. And there are so many different ways to try and visualize this information, and so a lot of what I'll be showing you today is basically just results. Okay, and then the tree ring part, dendrochronology. Tree rings offer a glimpse into environmental conditions throughout a year. So as trees grow, they put on new wood, and then if you were to take a little sample, which is what I'm doing in this photo here, it's like a little, kind of like a blood test, I guess. And that can tell you, based on how dense the wood is and how thick each ring is, can tell you maybe the conditions it faced that year. If it didn't grow a lot, maybe there was some kind of stressful event happening, so it was focused more on maintaining its health or surviving rather than putting on new growth. And this can put dendrometry into perspective. If these trees are 400 years old, but we only have electronic records going back like 7 years, there's a lot of time that is not being acknowledged there. But if we can take a sample and go back even as far as when the tree was born, so to speak, there's a lot of history that we can glean from that. So there are 2 different distinct colors that you can see in this image right here. We have this darker latewood band, and that is because it's added during the summer months as the temperatures might get a little warmer, so maybe growth slows down, or maybe the tree is running out of water reserves. So essentially the net effect is the same, that growth slows a little bit, and therefore the cells are a little bit smaller and more densely packed, and that's why it's darker. And since this late wood is added in the later months, it's especially helpful for studies like ours that are focused on heat impacts, since later in the summer tends to be more hot. And each core is about 5 millimeters wide or so. And I have this top photo here, because this is our discovery tree, which is like one of the oldest ones. And so this is the bark right here, and each little band represents 1 year of growth. So you can see just like absolutely hundreds and hundreds and hundreds of bands, which I think is really cool. Okay, so then the second part of my research question is looking into the relationships between tree growth and microclimate. So there are different ways to measure microclimate. The types that we will be focusing on are upper canopy measurements. So most of the tree's photosynthesis is happening through the leaves, and as you can see in this photo here, there are not a lot of leaves on this tree trunk. They're usually more up top, and that gives a more accurate reflection of leaf experiences. If the leaves are doing the photosynthesis, then it's more helpful to know what the microclimate is like at the leaf level, rather than more standard or other commonly used heights for microclimate measurements, which would be like 1.5 meters up off the ground. So our canopy measurements are like 56 meters up off the ground, which I wrote down as like over 150 feet or something like that. And so one big issue with microclimate is that it's just all interacting. So it's really hard to assign different tree responses with different microclimate metrics, but there are some trends that have been established in the literature. So moisture stress driven by temperature, for example, can exist even after a rain event. So if it was really hot and dry and then a rain event happens, that heat stress can persist even after the rain event. And during the heat dome itself, really severely high air temperatures were more common and extreme than the severe drought. And we'll look specifically at some proof of that. Okay, so one of the more important microclimate metrics that we are focusing on is vapor pressure deficit, which is the difference between how much water can be held in the air versus how much water is actually in the air. So that's saturation vapor pressure minus the actual vapor pressure. And those two things are dictated by temperature and humidity. So a higher VPD would mean that there's a larger deficit, which means that there is more space or more capacity for water to be held, which ultimately increases tree stress because there is less available water, relatively speaking. It's not immediately connected to water in the soil because it is atmospheric, and there are different types of relationships driven by atmospheric drought, which is driven by this stuff like BPD, versus soil drought or water that's literally available in the soil. And since warmer air can hold more water, VPD is primarily driven by temperature. Another metric that we use try to acknowledge both atmospheric drought and soil drought through what's called the Hydrometeorological Dryness Index, which is very simply BPD divided by soil moisture at 50 centimeters in the soil. There are different depths that we have available, but the definition in the literature uses soil moisture 50 centimeters below the ground. Okay, so next is defining stress. With so much data, it can be helpful to identify stress thresholds so that we can have a clearer perspective of lots of data. So if we say that a stress threshold is the point at which plant performance declines, we can use some guidelines in the literature to set different thresholds. So for temperature, both air temperature and leaf temperature, our stress threshold is 35 degrees Celsius, which is 95 degrees Fahrenheit. And we established this through stress degree hours, which is something that was established in the literature where you take your data and you summarize it to an hourly level. And then whatever that average hourly temperature is, you subtract your stress threshold. So for us, it's 35 degrees. So let's say the air temperature was 40 degrees. If we do 40 minus 35, that 5-degree remainder is our stress degree hour. And so this is just air temperature over time since January of 2019. So our heat dome is right here. So you can see that's a pretty significant spike relative to the rest of the data in our record. And then I also have these 3 bands for different fire events that happen that could be contributing to some of the results that we're seeing, or like Mark said, could have influenced our ability to collect some data. So for vapor pressure deficit, or this measure of evaporative demand, that stress threshold is 3 kilopascals. And again, you can see it looks similar to the air temperature cycles, which makes sense since air temperature drives VPD. And then lastly, for our HDI, or hydrometeorological dryness index, as our combined metric of evaporative and air temperature stress, our threshold for that is 35, and then this monstrosity of a unit. Okay, so anyone know something? Look at this graph. We're looking at graphs today. We're looking at so many graphs. Mainly, we're going to be looking at the accumulations of these stress metrics for the microclimate, and then we're also going to look at the results of our dendrometers and tree rings, and then we'll kind of summarize it all up. And with 11 trees and 7 years and so many other things, I will not be showing you everything that I have. We'll just be focusing on 1 or 2 trees across 1 or 2 different years. So let's start by looking at rain. We talk about how drought and heat correspond with one another, so it's important to know all of this. Water and precipitation is usually measured on a water year scale rather than a calendar year scale. So the water year starts the October before the calendar year. And that's because when you get fall rains, like I said, in a Mediterranean climate, the summers are usually dry, and then we usually get rain starting around September or October. Those precipitation events in the fall influence everything else for the spring onward in terms of water availability in the plants. So it's important to have this water year perspective rather than just a calendar year perspective. So this red vertical band right here corresponds to the length of the heat dome, so 3 days, June 26th through 28th in 2021. And so if we look at the corresponding red line right here to 2021, if we're looking at the full water year scale, it wasn't the worst in terms of drought. There are some papers that have said that drought was one of the most impactful drivers of why the heat dome was so severe and so deadly. But our data indicate that at least the year before was worse from a drought standpoint, but spoilers, 2020 was our best year for growth in our limited record. If we do a zoom in on just the spring and summer precipitation though, we can see that 2021 was the most severe in our limited record, meaning that there may have been a lot of fall rains in the spring leading up to 2021, but starting March 1st, it was really, really, really dry when the tree was actually starting its growing season. So basically when the water mattered the most. So 2021 is a year to focus on, obviously, and then I also want you to, as we look through these other figures, I want you to focus on 2020, which is this orange line. Okay, so then, here are the cumulative stress metrics. So as I mentioned, so this y-axis is the sum of degrees above our stress threshold. So if the mean hourly temperature was 40, like we said earlier, there would be like a 5 right here. So that's what this is saying. So all of this is the sum of degrees above 35 at this hourly scale. And this vertical dashed line represents the onset of the heat dome, so June 26th. And so these are just calendar dates where each line represents the different annual summary or accumulation. So things were okay. There were some heat waves minorly in the spring leading up to the heat dome. But once the heat dome started, it's basically just all terrible and all hot. And so it's a huge spike that is completely unlike any other year before or after in this limited record. And then it just wasn't even done. It said, okay, I'll give you like a month, and then I'm gonna be terrible again. So it was a bad time to be a tree, I guess. And then again, I want you to focus on 2021 and 2020. So from a temperature standpoint, 2020 was pretty okay. And then if we switch to vapor pressure deficit, it looks a little bit different, which is just to show how there's so much variability in the different things that these metrics represent. So if there's a huge difference in temperature between 2021 and the next highest, which is 2022, there isn't as much of a difference with VPD. So 2022 and 2024 kind of got close, but still 2021 was by far the most severe in terms of accumulated VPD stress. And you'll notice that 2025 ends abruptly at October 1, and that's just because that's when we ended our data collection. We decided to end our data collection at the start of the 2026 water year, just based on what was available and what time was looking like. Okay, so again, pointing out 2021 and 2020. And then lastly, our cumulative stress HDI hours. You'll notice that 2022 drops a lot relative to the VPD and the air temperature, and that's because if we look at the precipitation, 2021 had an extremely wet spring and summer, and so when we combine these stress metrics of evaporative stress, atmospheric stress and soil stress, this really shows that interaction between the two to cause a shift in these rankings. But still, the general trend is the same, where 2021 is the most stressful and most severe, and 2020 is pretty okay. So now we are done with microclimate, and we are going to look at actual tree growth. So this is one of our old growth Douglas fir trees, and this is showing interactions between growth or expansion and microclimate. I want to prioritize the use of the word expansion since, as we talked about earlier, you can't really know for sure whether expansion is due to permanent growth or just water swelling. But this green line here is our expansion curve, and the unit is cumulative basal area increment. So basal area increment is like the addition of new area if you were to look at like the cross section of a stem. And it's cumulative to look at how it would be if we were just measuring circumference. And the reason I didn't just use circumference is because basal area increment is both more common in the literature and also the unit of our tree rings. So in order for them to be compared equally, that's what that's all about. So this is a typical shape of expansion during a good season and a good year. So this is 2020. Of just the growing season, also known as April through August. So we start a little before May or so, and then we go up, and then expansion plateaus around the end of summer. And then it kind of starts to go down again, maybe because we haven't gotten our fall rains yet, but it's still hot, so maybe the stem is starting to shrink as it's losing more water. This purple line is the modeled daily expansion rate, also known as the first derivative of a Gompertz curve. So where it peaks up here represents the timing of the estimated maximum expansion rate. And so that's going to be like a little before June 1 or so. And this gray line is our maximum daily hydrometeorological dryness index. So you can see it's pretty low, and then it gets a little high as we get toward the end of the summer. And then these blue bars are our daily precipitation. So you can see there's quite a bit of rain before July, and then it gets dry as the HDI increases correspondingly, and we also get that expansion plateau. So if this is a typical shape, what did 2021 look like? And I will say that this tree ID 310, our old growth Doug fir, did have the most severe response. So this is what that looks like, where we have an earlier peak of expansion, and this growth rate modeled line is more narrow, so that could indicate maybe a smaller growing season window for that year. Our most severe timing of the heat dome corresponds to this HDI peak right before July, as the heat dome is happening, and that corresponds to an immediate drop in cumulative basal area increment. So the stem has contracted a lot immediately during that time. And while we would still expect some expansion after July 1 as is seen in 2020, it basically crashes and says, no, I'm done. I'm not doing anything else. And HDI stays high. So as we talked about earlier, it not only was severely, extremely hot during the heat dome, but then it stayed hot and just continued to be stressful. So there's a lack of summer expansion here versus 2020. That should say 2020, not 2019. But yeah, so that is important as we talked about earlier with late wood versus early wood. So if we were to look at the late wood band here, we expect that it would be very small. This is zooming in on just the heat dome effects. So remember earlier we talked about the 3 different types of stem cycles, stem expansion cycles. This is showing that just for 2 weeks before and after the heat dome. So we have some increment, which are these blue dots, and it's like growing. And then it takes about a day, but starting like a day or 2 after the heat dome event, we see the crash. And then afterward, it says like, okay, I guess we can do this some more. And it starts to expand again, but now the dots are green because it hasn't exceeded the prior maximum. So if it hasn't exceeded the prior maximum, then it's expansion. If it does exceed the prior maximum, then it's increment. And you see we don't have increment for at least 2 weeks after. And for this specific tree, that's true for the remainder of the growing season. So if we think about how this compares to other years based on our dendrometry record, 2021 would have been a fantastic year. And then after the heat dome, it completely crashed and continued to do so for the rest of the year. But 2020 was our stellar year, at least in the short-term record, across almost all of our trees. It had the best growth. And as we saw, it had really low stress conditions. So this is supporting that relationship between growth and microclimate. If we look at the tree reign records, this is going back 75 years, and this is the same tree, 310, an old growth Doug fir, where this purple line represents the year of our lowest basal area increment, which makes sense as the tree might still be, well, I guess it really wouldn't be that young. But in this record, that's the lowest. The green line is our highest BAI year, and then 2021 is the year of the heat dome. So if we zoom in on just the last 10 years, and also look at the distinction between early wood and late wood, after 2021, things are just declining. So this might indicate some carryover effects, either from the heat dome itself, or the climate has mainly returned to pre-heat dome conditions, but there have still been some stressful years relative to before then. So if we just look at other trees, this is just 6 of our dendrometers with the full 7-year record. Not all 11 do, only 6 do, with these band dendrometers. So these orange boxes are the years with the least basal area increment, so the smallest amount of expansion for that year, and then the blue boxes have the highest. So this is just confirming that 2021 was a fantastic year. 2019 was a not so great year, even though it was very similar to 2020 in just basic microclimate. And then 2021, for one of these old growth hemlocks, had the highest expansion. And so this is just showing that there are a lot of things that influence tree growth. And it seems that there might be some evidence of recovery as well if 2021, in the grand scheme of things, wasn't the highest or lowest. And this is another argument for carryover effects, because I mentioned 2019 and 2020 were really similar, but 2019 was way worse for expansion. And that could be because there was a heat wave in 2017. So maybe there are some indications of carryover effects there. And this is to go and show that there's evidence of both resilience and vulnerability. Of 2021, and like I said, in the grand scheme of things, wasn't the worst year on record. There might be some evidence of resilience there, where these trees can have a really acute and severe response. Or like I said, since 2021 started out as a really good year, maybe it could have been even better, but the heat dome just didn't have it in the cards for that year. So there's definitely vulnerability in what we've seen, and this is a photo of different degrees of foliar scorch, where the heat is so high that it's killing these leaves, which means there's less needles on the tree to conduct photosynthesis. And these results vary by everything, by species, age, site, other environmental factors. So it's like, if only there was a way to account for these and kind of try and see what expansion is like without the influence of all of these other things. And that's where modeling comes in. So we fit a linear statistical model on 6 trees, our Douglas fir trees, for the same period that we saw earlier of the heat dome, plus or minus 2 weeks. And we did 2 years before the heat dome year, 2 years after, and used mean daily basal area increment. And this is addressing those other influencing things. So this is just to show our periods, what we're calling periods. So 2 weeks before the heat dome itself, and then the 2 weeks after, across 5 years. So we have our periods, our calendar dates, and then we have our year groups, where we take the average of the 2 years before and the 2 years after and compare that with 2021. So these are results of the model, where this line, this horizontal line at 0, is important for assessing, we could say, like, statistical significance. So if it crosses 0, then that means we can't really say with confidence whether that metric is significantly different from other things or not. So in this instance, we are taking the average daily basal area increment in each period and subtracting the value in the before period from it. So this is explaining, like, if we say that basal area increment during the heat dome in the years before 2021 is like 1, and the basal area increment in the before period is like 0.5, then that difference would be 0.5, which is what we can see here. And they can be kind of close to 0, since this is such a small 4-week window of time. There might not be that many differences in daily basal area increment or rates of expansion. However, we see this part really sticks out right here. And this is taking basal area increment during the actual heat dome itself, since it's the year 2021, and subtracting basal area increment in the 2 weeks leading up to it. This is a very negative number, which means that there was contraction during the event. And this is extremely significant and very, very much departed from all others. And so this is confirming our observed results, that even when modeling and accounting for all of these other confounding variables, the heat dome events and effects were still different and still significantly different. And then comparing the 2 weeks after to look at immediate recovery rates, it is still lower. Daily basal area increment in the 2 weeks after the heat dome is still lower than daily basal area increment in the 2 weeks leading up to it. There's so much more that can be said, but we're gonna look at some take-home messages for now. And so these are like, if you don't get anything else from this, these are the things that I would love for you to remember about my work, which is that there were unique and completely uncharacteristic spikes in temperature and temperature-related microclimate metrics during the 2021 heat dome, and that corresponded to an immediate and, in many cases, severe shrinkage of stem circumference across all of our sampled trees, but with varying severity. During the heat dome itself, and for at least 2 weeks afterward, our modeled estimates of daily basal area increment were significantly different and also lower compared to the same calendar dates of different years. And there are mixed results in the recovery since 2021, but most trees are continuing to decline, even if the climate has been just hot or just dry. And these analyses correspond with basal area, both calculated and observed from our tree rings. So based on those observations, we can infer a few things. We already established that there's evidence of both vulnerability and resilience as basal area increment drops during the heat dome, but recovers with variable independent tree responses. You cannot fully predict BAI with any one singular microclimate metric, but the metrics that we do have are trying to capture different aspects of heat and drought stress. For example, the soil drought stress versus atmospheric drought stress. And even summarizing these 5-minute increments of data to daily resolutions still provide really detailed insights and stories that can be supported by tree rings. And we hope that future research builds upon this framework of data integration ranging from minutes to years, and also from soil all the way up to like 150 feet up in the tree. So research like ours, this is like the closing line in my conclusion of my thesis, that research like ours may better prepare forest managers, policymakers, and other community stakeholders to adjust to a rapidly changing world. And that's like it for now. I said a few things. Now we're done with the school stuff, and now we're on the like gushy stuff, the sentimental stuff, where this work would be impossible without my village and community of loved ones, as well as my committee and other helpful experts. So you already heard from Chris and Mark, and then other important people in my committee and in this process include Lauren Albert, Matt Powers, Amanda Brackett, and Dusty Bannon. HJA research like mine was administered cooperatively both by OSU, the USDA, Forest Service, Pacific Northwest Research Station, and the Willamette National Forest. And this research was funded by a grant from the National Science Foundation, and there's the name for it in case you care, and then also the College of Forestry. And so please email me. This is a QR code with more information and references cited, including pictures of my cat. And then, after questions, there's, like I said, that really short 3-minute like summary video of my time. But yeah, thank you. All right, I'll take questions, if you have any. Yes?
I have just kind of a hypothetical question. The heat dome came as a surprise. We had a couple days warning. We knew it was coming. And I was going to ask you, with what you analyzed, what did you wish we had done at that time when we were starting to get a message from the National Weather Service that we were going to come into this unprecedented heat? What would you wish we had gone out and either installed or pre-measured before it hit and after? Is there anything that you can think of you wish?
Do you mean like
the crystal ball?
Do you mean like things that would have helped data analysis, or do you mean like preventative measures?
No, more things that would have helped with us understanding the impacts of the heat dome.
Well, I keep asking Mark and Chris if we can install more dendroners. I think the biggest thing is just to have more information available. Also, if there were more soil moisture sensors or an establishment of the specific soil type at the Andrews, that could be helpful because it was a little challenging trying to define a stress metric for soil moisture since specific records of the specific soil type could be a little hard to find. I think there was plenty to work with, but in a crystal ball scenario, I guess those are the things I would say.
Okay.
Yeah.
Thank you.
Yeah, of course. All right, I'm gonna see if there are questions on Zoom.
Oh, someone asked if you could repeat the questions for those on Zoom.
Oh, the question was, if I had a crystal ball, what are some information that I wished was available at the Andrews before the heat dome hit for better data analysis? Okay, well, oh, yes,
Nice job.
thank you.
Congrats. I had a question about your plots on the rate of maximum increase. You mentioned that in 2021, the peak maximum increase happened earlier and in the year and before the heat dome. And I guess I was wondering, since obviously the trees didn't know that a heat dome was coming, if there was another indicator that year that maybe trees were responding to, was it generally warmer before the heat dome, or?
Yeah, that's a great question. So the question is related to this slide where we have this earlier peak of maximum expansion that happens before the heat dome hits. So what was contributing to this happening? If we're comparing just these 2 years, there were some precipitation events happening, but there were not as many. And also, like we looked at over here, there were some more spring heat wave events happening in the beginning of June, so that could have been contributing to that as well. And it's also important to note that this is just a modeled expansion rate. And so yeah, there are a lot of things that could be influencing that as well, but that's the first thing that comes to mind.
Yeah, I'm curious. Have you done any thought experiments using the second growth trees in particular, like looking at sort of opportunity cost or what they've lost over, after the heat dome, and then projected that out to say some 1 hectare stand of Douglas fir or something, and I don't know, make that relevant to the timber industry or something like that.
Oh, yeah.
If this happens more frequently, this is what we might be losing in terms of growth, and just taking those results and doing some sort of fun simulation thought experiments.
Yeah, that's a great question. So the question is comparing some of the results that we've looked at today and thinking specifically about younger trees or second growth trees, since in the timber industry, that's usually what's used. And if I have insights or ideas on how this could be used in an applied sense for the timber industry. I thought it was really interesting that from a literature perspective, older trees should be more resilient to climate change compared to younger trees. That's not really what we found in this, albeit limited data set. And I was thinking about why that is, and a lot of the literature actually compares old growth trees to baby trees or 20-year-old trees, not what is still considered relatively old compared to that. But I was thinking about what these numbers of basal area increment actually mean in an applied sense, like you were saying. And so in our model, this drop that stands out of everything else, the numerical version of this estimate is a drop in 0.82 square centimeters per day. And with a lot of these older trees, their actual basal area, so not just the increment, but the basal area of the cross section of the tree can be upwards or beyond 3 square feet. So in a very limited sense, 0.82 square centimeters per day might not sound like a lot, But when these are really big trees and this is a response in just one day, I haven't done the math, but if I were to take this over the course of like a few weeks, I imagine there would be a pretty sizable effect, especially if we're talking about a tree that's like 150 feet tall, and we take that basal area and like scale it up to the height of the tree. I think that there's probably a lot of biomass that's being lost by a stressful event like this.
Yeah, you mentioned late wood and early wood, and that maybe the late wood was lessened by the heat dome effect. Did you see or take a look at any differences in like the ratio of like late wood to early wood across these years, or to try to get, be kind of a fussy thing to do, but maybe get the density of the ring and see if that kind of changed them?
Yeah, that's a great question. Thank you. So the question is about early wood and late wood, and trying to think about other ways of measuring or acknowledging that, maybe even like wood density. The perhaps embarrassing answer is that I still have to do that. It is on the to-do list. But we have access to blue light reflectance measurements, where you scan the cores and you have like a little color box that calibrates it, and the scanner flashes blue light at the tree cores, and it results in this like gradient of different shades of blue, and that corresponds to the wood density. So it definitely is something that we can measure, and that I have started measuring, but you know, time. But we do, so this figure is just in the last 10 years, but we have figures for this for each tree for the full time series as well, or at least within the last 75 years. But even just looking at this, late wood is smaller than early wood, which we would expect since it is, we already talked about that, but even starting in 2021, it stays pretty low. And we talked earlier about the heat wave that happened in 2017, so we can see a spike in late wood for that year as well.
No, in Corvallis, I've noticed that just looking at the HISLOP data for the area, that I think the last 13 or 14 years, summers have been hotter than their normal, practically every single one.
Yeah.
So maybe we've kind of moved into some more stressful times in general.
Yeah, I could believe that for sure. Thank you. Any other questions?
There's a question online.
Oh yeah. What do we got? Okay. We have a question. Does the shrinkage correspond to loss of water only, or also metabolism of tree tissue? That's a fantastic question. One of the answer is that I don't know. One of the possibilities for future work is really specialized physiological measurements that do explicitly measure like the rates of cell division in the tree and things like that. So I think that is a great future research question, but it is not one that I have asked myself. Thank you, Devin. Any other questions?
If there's no more questions, let's thank Abby again. And please join us at Squirrels at 5 p.m. or so if you're interested and able to. Thank you. Now we get to grill our closing session.